The four most common types of chemical conversions involve moles, grams, and molecules, and they are mole to mole, one step, mole to gram or gram to mole, two steps, gram to gram, and gram to molecule conversions. We showed the first two in the previous screencast, and we're going to show the next two in this screencast, gram to gram and molecular conversions. Now, of all those types, gram to gram are by far the most common because that's where you really have a balance and you can do the chemical reactions. Notice how practical this is. The combustion of 100 grams of butane, imagine a big lighter with all sorts of butane in it, with plenty of oxygen, and that's usually the case, right? You're burning it in the air. It doesn't limit the reaction, so we don't worry about it. We'll make how many grams of carbon dioxide? I like this, right? Everything's weighed, everything's actually doable. How do we do these? Well, we recognize that gram to gram conversions are three-steppers, and what do you start with? What you're given, the 100 grams of butane. I would also put equals blank grams of CO2 to remind yourself where you're going. And we're going to find out how many grams is a mole, and 58 grams is a mole. We need that because every time we react a mole of butane, it will make 4 times as many moles of carbon dioxide. So we've got a little less than 2 moles, but we're going to get a 4-fold increase when this thing gets chopped up and makes 4 moles of carbon dioxide for each mole of butane. And of course you could write 1 and 4 here if you want. And now it didn't ask us for moles of carbon dioxide, it asked for grams, so we'd have to convert it. And a mole of carbon dioxide has a mass of 12 plus 32 equals 44 grams. We're using whole numbers. Be aware that when you're solving a problem, you should give it to the correct level of precision. Here we're more focused on just getting the process done correctly. And this will, once we punch it in, produce 303 grams of carbon dioxide. Here's another one. You got a pound of butane. Okay, great. That is a big lighter. We got plenty of oxygen again, and this time we'd like to know how many moles of water it makes. I'm noticing a 5-fold increase. Start with what you're given. It's 3 steps. I'd go ahead and write grams of H2O so I don't go to CO2 by accident. And I'd say to myself, 58 grams of butane is a mole of butane, but every time I react a mole of butane, it produces 5 times as many moles of water. See the mathematical precision. They're canceling, and I'm going to cancel again. The mole of water is equivalent to 18 grams of water, and this will make enough water to produce 703 grams of it. Okay, last one. Sometimes they want to know molecules, and don't forget that the mole is not only something that can be massed out, but it's countable all the time because it is a number. And here's a relatively tough problem. You got only a microgram, a millionth of a gram, 10 to the minus 6 grams of butane. Wow, is that even a drop? We light it on fire and we wonder how many molecules of carbon dioxide it will produce. Well, it's interesting when you consider this because you might say, oh my God, it's only going to make a few molecules of carbon dioxide. Oh, you would be wrong, right? The mole is such a giant number. Start with what you're given. In this case, it's a microgram of butane. Now, if it were me, I'd probably write 10 to the minus 6 grams of butane because I know I need grams since, 58 grams of butane is a mole. Here we go. But I start with the microgram of butane, and I could go ahead and say there are 1,000,000 micrograms in a gram, or I could say a microgram is 1,000,000th of a gram. I did it this way. There's 1,000,000 micrograms in every gram of butane. That's just a memorization thing for micro. And a gram of butane, well, 58 grams of butane is a mole. And where are we going? We're going to carbon dioxide. So this is the 2 to 8, 4-fold increase. Every mole of butane chops up into 4 moles of carbon dioxide. 2 to 8 is the same thing. And they do want to know, no, look at this. They're not going to grams. They're going to molecules. So watch out there. You might go to grams by accident just because you're used to it. But just remember that the mole is a number. Every mole of carbon dioxide is a mole's worth. Avogadro's number, 6.02 times 10 to the 23rd units. And the units in this case are molecules, so write it out nice and neatly. Do a whole bunch of canceling out. Boom, 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 and boom. Note the diagonal nature of it, and then punch it all in. You could punch in the top, write it down, punch in the bottom, write it down. Most people, I think, punch it all into their calculator and then divide it by these things, but you got to use parentheses, generally speaking, or your calculator might PEMDAS it wrong, might do the order operations wrong. Regardless, double check it, and you should see that you're making more than 10 to the 16th grams of grams. That's not right. 10 to the 16th molecules of carbon dioxide. Make sure that you recognize that that's a typo. It should say molecules there. That's a lot of molecules of carbon dioxide. However, it's well short of a mole, right? So I doubt that it weighs very much. That's gram to gram and molecular conversions.